Okay, so I've now started the recording. So yeah, in answer to your question, homework is always due at the beginning of class. And I'm sure you guys can understand why I have to do it that way. Because the first thing we do in class is we go over the answers to the homework. So if somebody wanted to turn in homework late, all they have to do is just sit back and watch all the answers and then write them up and turn them in. And what good is that? That's no good. Okay, so I have to make the homework be due at the beginning of class. That's the only way I can do it.
I understand that.
Okay, so I see that when I asked you if you guys have got lots of homework, several of you have piped up here and say even more homework than if anything. Sorry about that, but I hope you don't think that the amount of homework that I'm giving you is more than normal. But anyway, let's get on with it. Okay, so here, speaking of homework, let's talk about today's homework. So here we go. All right, so here are the answers to today's homework, at least the answers that you haven't already looked up. Oh, okay, so Josh has quesadillas. Oh, I am jealous. Okay. And Cohen is saying technically it's all homework now. Ha, ha, ha. Okay. All right. So any questions about what you see on the screen right now? Or do you have questions about the other problems where you already looked up the answer? Anything where you weren't able to figure out how we got the answers we got?
Can we go over 29?
29. Okay. Let me get my glasses and remind me what 29 is asking. Ah, okay. 29 is a very good one. I'm glad you asked that. So yeah, the rest of you hold off on your questions here. Let's do them one at a time here. Okay, so 29 is actually one of my favorite questions. All right, so in fact, I was anticipating this. So here is a little picture to help us see what's going on. So basically what we're doing is we've got the Millikan oil drop experiment. And so what the book is saying here is they're saying that we got an oil drop in there and it's positively charged. So what it means is when they sprayed the little perfume bottle here, they hooked up something so that it stripped the electrons away as each oil drop passed through. So we got a bunch of positively charged oil drops. Most of them fall and they hit this upper plate, but there's a little hole right here, so that it doesn't show very well in the picture. But an oil drop has gotten down here. And so now, if you were to do a free body diagram on the oil drop, you'd see that you got gravity pulling it down, and you've got the electric force, which is holding it up. And this battery that you see here is not just a regular old battery. Some of you are talking here. I'm going to mute everybody here if you don't mind. Okay. All right. Okay. So this battery is not just a regular old boring fixed voltage battery. It's an adjustable battery. I have a bunch of them in my room. If we were back in my classroom, I could show you how it works. You turn a little dial and you can adjust the voltage. So what Robert Millikan did was he adjusted the voltage there until he got it to where the oil drop was floating, so that the downward gravity force matched the upward electric force. Okay, so we know what the downward force is. We know the downward force is, or the weight is 1.2 times 10 to the negative 14 newtons. Now notice it's in newtons. That's not the amount of kilograms it is. That's already been multiplied by G. So don't go by multiplying it by G a second time. So mg there is 1.2 times 10 to the negative 14. Okay, and it's suspended by some parallel plates where the distance between the plates is 0.64 centimeters. And the potential difference, which is another way of saying voltage. So the voltage is 240 volts. So we want to know what is the charge on the drop. Okay. All right. So we know that we can calculate the magnetic field. Let's see, did I have a slide here already for that? Hang on a sec. I think I might have had a slide already to go for that. These are all the slides that you guys are going to be seeing throughout the course of the day here. Okay, this one right here. Okay, so we know that the electric field in between plates, this equation rules it. Okay, so if we arrange it, we can get this. So we can solve for the electric field. Okay, and so now let me go back to here. So we know that the delta V is E times D, and we know what delta V is. They told us that, and we know what the separation is the plates. So that means we can then go back and we can figure out what E is. So go back to here. All right. And so we know, so we can then figure out what the charge is on the drop. Okay, does that make sense? So we know mg, we know E, so we can figure out what Q is. Does that answer your question?
I think so. I think it was asking about the excess electrons.
Oh, okay. Well, once we know the charge on it, so we know what the charge of an electron is, right? If we get out our book and look to the very last page, right up here, it tells us what the charge of an electron is. So if it turns out that when we calculate what Q is, if we get an answer that's 1.6 times 10 to the negative 19, we know we've got one electron. But if it's twice that, then we know we got 2 electrons. If it's 3 times it, we know we got 3 electrons. Okay, so so Yasin is asking on number 26 if there's air resistance. Technically, yes, there is. We're going to assume that the thing is falling so slowly that air resistance is negligible. But if we're going to be 100% correct, which, yeah, maybe we probably should, technically there would be air resistance. But it's going to be negligible, especially because the way that Millikan did his experiment was he purposely designed it so that the drop was just floating. So if it's just floating, then obviously you're not going to have air resistance for that. Okay, any other questions on the homework? No questions? Okay, I guess we'll move on then. All right, so new material. Let me jump past these. These are the ones that I anticipated your question. That's why I put these slides in there. Let's help answer that question. Okay, so let's see. Let me back up just a bit. Okay, so like I said in the quiz, which I hope you guys have all taken, I haven't yet looked to see. In the daily quiz after last time class, one of the questions was why do physics teachers love parallel plate capacitors? Okay, because you are going to see a lot of problems, not just tomorrow and next week, but for the rest of the year, actually. From now until the time that we end the class at the end of the school year, we are going to be using parallel plate capacitors a lot. Okay, and the couple of reasons for it, the one really big reason is because it makes the math doable by a high school student. Because as long as we have an object in between the parallel plate, you see how all those arrows are nice and straight and parallel. What that means is that the electric field inside there is constant, no matter where you are. In fact, let me back up just a bit here. Okay, so if this little ball here, if he was over here or over here or over here, if he's anywhere in there, he is going to feel the exact same force. And if he starts off on this side of the plate and moves his way down slowly to that side of the plate, all the way along there, the force on him is going to be constant. And so if the force is constant, that means that it's doable. The problem that we need to solve, we don't need to use calculus in order to solve it. Now, I realize that's a disappointment to some of you. Some of you want to use calculus. To those of you, let me just say, take the U of U physics class next year. You'll get a chance to use your calculus. Okay, so one thing that you can do with a parallel plate capacitor is build an electron gun. And this is something that your book does talk about, but not in this chapter. They push it back to a couple chapters back from now. And I think now is a good time to talk about it. So I'm going to go through how to build an electron gun. And I'm going to ask you questions in today's quiz about this. And it's not explained in this chapter of the book. So I highly recommend that you take careful notes about what I'm about to say, because there will be questions in today's quiz about how to build an electron gun. Okay. All right. So first thing we do is we take our good friend, the parallel plate capacitor, and we turn it on its side. So it looks something like this. And so I've got a battery down here. Now this one is a 9-volt battery, but obviously it could be any voltage we want. So when I connect one lead of the battery to the left side of the plate and the other lead to the plate that's on the right side, and remember these are these are not just lines, these are plates. These are, like something like this perhaps, but it's been turned on its side here. And I've got another one on the other side. Okay, so they now have charges on them. One has an excess of negative charges on it. The other one has an excess of positive charges on it. Okay, and I'm going to separate them by some distance. What you see right here is I've said 1 centimeter, but it could obviously be anything that I want. Okay, so let's just do a little bit of review before we get into the fun stuff here. I want to know what the electric field will be in between these plates. So this is a problem identical to what you had in your homework tonight. So I'm going to pause while you guys get out your calculators and think about it. So if I've got a 9-volt battery, and so that means I've charged up each plate here. So the potential difference, the electric potential difference between the two plates is 9 volts. The two plates are separated by a distance of 1 centimeter. So I want you to solve this exactly as if it was one of last night's homework problems. And I'm going to wait until somebody gets an answer here. You guys got to type something in. Okay, so I'm seeing 900. I'm also seeing 9,000. Interesting. So the two of you need to talk, except that'll be kind of difficult here. Okay, so it looks like a lot of people are saying 900. All right, it looks like we finally have agreement that it is in fact 900. Let's see what I got when I did the calculations. Hey, what do you know? I got the same answer you did. Okay, so now we know that the electric field in between these plates is 900 newtons per coulomb, right? So now, let's say that I've got an electron that's just floating there in between the two plates. I want to know how much force is going to be on that electron, okay? So again, I'm going to sit and wait while you guys do the math. We know what the field is. We know that the field strength inside there is 900 newtons per coulomb. If only we knew what the charge on an electron was. Where could we find that out? Anybody want to type that in? That might be helpful. What is the charge on an electron? That's a number that you guys are going to be using a lot, so you should know. It's in the back of your physics book. Okay, good. 1.6 times 10 to the negative 19. Excellent. Okay, so if we know the electric field and we know the charge, we should easily be able to calculate the force. Okay, so I'm waiting to see. I'm not seeing any answers yet. What is the force? How many newtons of force are going to be on that electron? Okay, I'm seeing an answer. I'm seeing 2 answers, and they are both the same. That's good. How about one more? Anybody agree or disagree? Nobody wants to speak up? Okay, well, I'll tell you what, let's see what I got. Okay, okay, Kiker just thirded it. Okay, and hey, what do you know? I got the same answer here. Okay, so, and I just did 2 sig figs. All right, so now we know what is the force that's acting on that electron. Okay, good. Let's take it to the next level here. Okay, so let's suppose that the electron starts out right next to the negative plate. Now, since the charge on an electron is negative and it's sitting next to a negative plate, it's going to get repelled. And in addition to getting repelled from there, it's also going to get attracted towards the positive plate. But you don't need to worry about using Coulomb's law. Just use the fact that it's in an electric field, and we know that the electric field is constant. And because we know the value of the electric field and we know how much charge is on it, we've already calculated the force. So that is the force that's going to be on it. Okay. So how much work is going to be done by the electric field when it pushes it to the positive plate? This one I hope you guys would get easily, because what's the definition of work? It's what times what? Work is force times distance. So we know the force, we know the distance. I'm thinking we could probably do this one without even a calculator. I'm not seeing any answers yet. I'm not going to move on until we see some answers. Come on, guys, you don't need a calculator to multiply by 0.01. Okay, good. I'm seeing some answers. And the answers agree with my answer. Okay, good. Okay, so if that's how much work we did on the particle, then how much energy is that particle going to have afterwards? Because it started off just sitting there, not moving. So it has 0 kinetic energy. So we've done 1.4 times 10 to the negative 18 joules of work on that thing. So when we're done, do you not agree that that's how much kinetic energy it's going to have? That makes sense? Okay. All right, so if the work done on it was 1.4 times 10 to the negative 18, then that is how much energy it's going to have. And the energy is all going to be kinetic because it's all moving horizontally here. We don't have to worry about gravity. So my next question, which you can see right here, how fast is that baby going to be moving when it hits the positive plate? If only I could remember what the formula for kinetic energy was. Well, that was months ago.
1/2 mv squared.
Ah, thank you. 1/2 mv squared.
An electron.
Okay, very good. All right, so we're going to need to know what the mass of an electron is. You are correct, Josh. If only I had some place I could look to find out what the mass of an electron is. Oh my goodness, what's this? There it is right there. It's in the back of the book. Okay, so 9.1 times 10 to the negative 31 kilograms. Okay, so the mass of an electron. And let me write that down. That might come in handy because I don't think I wrote it down here. So while you guys are doing that, some of you probably already have answers. Okay, so mass of electron equals 9.11 times 10 to the negative 31. And let's make that be superscript. Oops, not that one. Not that one. This one. Okay. All right. Very useful information. Okay, so Ian's asking, don't electrons have no mass? Oh, electrons very definitely have mass. Are you perhaps thinking of a photon? Photons are the things that don't have mass. And we're going to be talking a lot about photons in a very short amount of time. Not next week, but after that. Okay, so I'm seeing an answer here. Let's see if we get a couple more people also have answers. So Josh is claiming 1.2 times 10 to the 6 meters per second. Does anybody second his motion? Or does anybody disagree with
I'm not sure how he got that, though.
Say that again, Jared?
I'm not sure how he got that.
We're going to talk in a minute about how he got it. Okay, so Ian is agreeing. All right, let's see what I got when I did it. And also, to answer your question, Jaron, let's see how I got it. Okay. All right, so this is how I got it. So I'm saying that I know that the kinetic energy is 1/2 mv squared. And I know that the kinetic energy is 1.4 times 10 to the negative 18. So I take this and I just do it a little bit of algebra, which I'm sure everybody's good at. Okay, so when I rearrange this, I get this equation right here. So I get a different number than Josh got. Oh, he forgot the 1/2. Bad boy, bad. Okay, so somebody want to second my motion here? Because as you know, I do sometimes make mistakes. When you put in the 1/2 properly, do you guys get the same answer I got? Okay, good. All right, excellent. That's reassuring. Okay, so that electron is now moving at 1.8 million meters per second. That's million, okay? That's incredibly fast. And remember, we were just using a wimpy old 9-volt battery to do this. So how is it that you can get an electron moving so incredibly fast, 1.8 million meters per second, with just a wimpy old 9-volt battery? Why is that? I need to see some answers. Because it weighs almost nothing, exactly. So even with a very tiny force, you can get that baby moving really fast because it has so very little mass. Okay, so we're making progress on our electron gun here, but we don't have a very useful gun right now because nothing comes out of the gun. You know, when we connect up the battery here and turn on our gun, pull the trigger on our gun, nothing comes out. Anybody have any suggestions on what we can do to make it so it shoots stuff out? Yeah, Yasmin is saying rats. I agree, rats. Put a bullet in it. Okay, darn it. Come on, I need some useful comments here, guys. How do I get that electron to come out? You guys are going to kick yourselves when you.
Maybe like a negative plate on the bottom or something.
Or how about something even simpler? How about we get out our drill and we drill a hole in the plate? Okay. Okay. So, all right. So this is all we have to do is if we just drill a hole in that plate, then that'll work. So any electron that's in here is going to feel a force that accelerates it over here. Now, most of the electrons are probably going to be down in this region here. You guys, okay, yeah. So any electron that's down here, it's going to come over here and it's going to go plunk. It's going to hit the wall. But any electrons that are in the right spot here, they're going to get accelerated. They're going to come out here and they're just going to come shooting out here. And if we use a 9-volt battery, they're going to come out at 1.8 million meters per second. Okay, so now we've got an electron gun. Now, there were a lot of steps that we went through just now to calculate that. I wonder if only there was an easier way we could have done that. Well, it turns out that there is an easier way. And because you guys all did the homework and I trust that you all actually understood the homework, if we use some of this, what we learned in last night's homework, we could calculate what we just did a whole lot more easily. Here's how we do it. Oh, so Annie is asking what use does an electron gun have? A lot. We're going to talk about that in a minute. But put that on hold for just a sec. But the answer is it has a tremendous amount of use. So just be patient, I'll tell you. Okay, let's see if we can figure out that speed more easily. Okay, so we know that the definition of voltage is work divided by charge. So if we do a little bit of algebra there, we can rearrange that so that we get work equals the voltage difference across the plate multiplied by the charge. We know that the work is equal to the kinetic energy. And so that means that's how much kinetic energy the thing is going to have when it comes shooting out. And we know kinetic energy is 1/2 mv squared. So that means then the 1/2 mv squared is equal to delta V times Q. So now we just do a little bit of algebra. Now, one thing you do have to be careful of, we got a lowercase v over here, and we got an uppercase v over here. We got to be careful. There's potential for confusion there. The lowercase v that's that's our velocity. The uppercase V with the delta in front of it, that's our voltage. So be careful, don't get those two mixed up. Okay, so this equation right here could have given us the answer. We didn't need to calculate what the force was. And the interesting thing that a lot of people are really surprised when they hear, we didn't need to know what the distance was between the plates. It didn't even enter into the equation. Okay? So we could have taken our 9-volt battery and we could have connected it up to a plate that's 1 centimeter apart, or we could have connected that same battery up to plates that were 50 centimeters apart. That electron is going to have the exact same velocity when it comes shooting out. Okay. Now the reason is because the electric field in here is going to be stronger because they're closer together. And so you get a stronger electric field over a shorter distance. Over here, you get a weaker electric field over a greater distance. They cancel each other out. Okay? So come back up here again. So all we need to know is what is the voltage on the plate. We don't care what the distance is between the plates. Okay, so Yasna is just asking me to go back. Is this where you wanted me to go, Yasna, or do you want me to go further back? Okay, good. All right, so everybody got that? This equation, or these equations that you see on the plate on the screen right now, these are very important equations. You are going to be using these again and again and again for the rest of the school year. So maybe we could start calling this our new favorite equation. Seems like every couple of weeks we get a new favorite equation. All right. Okay, so let's go back to here. Okay, so I haven't forgotten the question about why would you want an electron gun. Don't worry, I promise I will get back to that. But before we get to that, there's still something about our electric gun that I would hope that some of you are wondering. And that's, where do we get the electrons from? Because how is it that we get an electron in here where we want that electron to be? Okay. Well, the answer to that is given by this. What we're going to do is we're going to take our negatively charged plate and we're going to put a very sharp point on it. Okay. Now you might wonder, why do you want a sharp point? Well, think about this. If you've got a quote unquote normal parallel plate capacitor, notice how the electric field lines inside the capacitor, they're all uniform, they're all equal. No matter where you are in between here, you will feel the exact same electric force. Now, if you get near the edges, okay, admittedly, things get a little weird on the edges, and if you get outside, it's definitely weird. But as long as you stay inside, in between the plates here, you've got a nice, normal, constant electric field. But if you have a sharp point there, that changes everything. What happens is that sharp point intensifies the electric field at just that one point. And in fact, if that electric field is really, really sharp, or I'm sorry, if that point is really, really sharp, the electric field at that point will become so very intense that it can pull electrons right out of the metal. Okay, so that's what you do is you make that point there, and you charge it up so you get an electric field. Now everywhere else the electric field is pretty uniform, but right at that point you get a very super difficult one, or super strong point there. So Yasna is asking, wouldn't that make the math be different as it's not parallel anymore? Yes, you are correct. So now all of the math that we do is now only going to be approximations. But when that electron comes out, okay, it pops out. But you see, the electron, it doesn't have to move very far before it gets into an area where the electric field is relatively uniform again, right? So as long as the plates are separated by enough of a distance, this tiny area in here, where the electric field is not uniform, it's a small fraction of the total distance. So you see, it makes sense that we can pretty much ignore it. Now, it is true that the calculations we get are going to be a little bit off, but they're going to be close enough that that'll be good enough. Okay, so we get that really strong electric field there. It has pulled a couple of electrons out. okay? And so now all these electrons are coming out and they're getting accelerated towards the right. Now, most of the electrons are going to be down here and they're going to hit the plate and go thunk and nothing's going to happen. But some of them are going to be in the right place. And so these electrons are going to come shooting out. They're going to go right through the hole. And bingo, we now have an electron gun. Okay, so now let's get back to the question that somebody asked. I don't remember who it was that asked. They said, why would we want an electron gun? Well, you guys, do you remember the old style TVs, or have you, I mean, flat screen TVs are pretty much all you can buy right now, but do you remember the old kind of TVs, the ones that are, you know, the opposite of flat, that are really, really big? Okay. Yeah, the thick ones. Yeah. Well, you know how they worked is they had an electron gun. Okay. So what would happen is on the back end of the TV, the part that's stuck out, remember, some of you may remember there's a part that actually sticks out behind the TV. That's where the electron gun is located. Okay, so it comes and it shoots electrons out. And then as the electron travels along here, you can steer the electron by taking another set of parallel plates. I probably should have prepared drawings for this. But so imagine you've got an electron zipping by here. So here I am, I'm watching the electron go zipping by. I hope you can all see the video. Okay, so this electron is going zipping by. If I were to take two parallel plates right here, so again, here's yet another use of a parallel plate capacitor. So I'm going to take two plates right here. As the electron is zipping by, if I charge up those plates positively and negatively, I can make it so that electron will not go in a straight line, but I can steer that electron. I can make it either curve down or curve up, okay? And then on the front side of the TV, I have that glass screen. And what I do is I coat it with something called a phosphor. So when the electron hits the screen glows. Okay, so I can shoot these electrons at the screens. And so if I have one set of parallel plates that can steer the electron up and down, and then over here I have another set of parallel plates like this that can steer the electron left and right. So then between those two pairs of electron plates, I can make that electron hit the screen anywhere I want it to, and then the screen will glow. And then if I just scan the electron across really quickly, I can create images there. So old style TVs are a great example of electron guns. Okay, so Ian is asking, is that why when you see videos of old TVs, they look like they have lines moving down them all the time? Actually, you're not too far off. Now, in reality, what's happening is the lines are moving so fast, you shouldn't see them. So Cohen is saying that's why they needed screensavers. Absolutely, yes. Because if you don't have a screensaver, if you just constantly have these electrons bombarding the phosphor, every time the electron hits the phosphor, it gives off some light. That phosphor only has a limited lifetime. If you just sit there and you just keep hitting it again and again and again, the phosphor is going to lose its phosphorescence capability. Okay, now, some of you might say, well, okay, great, but nobody uses those kinds of TVs anymore. So now why would we want an electron gun? Well, it turns out there are a lot of other applications. There's a lot of medical instruments that use electron guns. There are a lot of scientific instruments that use electron guns. And we are going to be talking, not next week, but maybe the week after, but very soon, we will be talking about a bunch of scientific experiments that have been done and that could still be done today, and that are still being done today, where the electron gun is key. If you didn't have an electron gun, you wouldn't be able to do these experiments. Also, electron microscopes. You guys have heard about electron microscopes, the things that let you see things that a regular microscope can't see. They use electron guns. Okay, so let's move on now. Okay, now here we're getting really fancy. Okay, what we're going to do here is we're going to take multiple parallel plate capacitors. So the one on the left here, okay, that one is the one that has the sharp point on it. So that's where the electrons come. So we shoot that out through here. So here's our first electron gun. Now our second electron gun, we don't need to worry about sources. What we do is we'll just do we'll drill a hole in both plates. So the electron that came out of the first gun comes in here. Now it's already moving pretty fast when it enters here. But what's going to happen is it's going to get accelerated even more by the second gun. And then when it comes out the third gun, it gets accelerated anymore. And in fact, what you can do is you can stack these one after another, after another, after another, and you can get these electrons moving at unbelievably high velocities. And many of you heard of something called a linear accelerator, particle smasher, whatever you want to call it, atom smasher. Okay, this is basically how atom smashers work. So you've heard of the Large Hadron Collider, perhaps? That's the biggest atom smasher in the world right now. This is how they do it. They take hundreds or even thousands of these guys. And yeah, it's Swedish. Yeah, it's right on the border between Sweden and France. In fact, it's so huge. Half of it is in France, half of it's in, actually, no, it's not Swedish, it's Switzerland. Sorry, it's Switzerland, France and Switzerland. And so, yeah, that's how they work. Okay, so you can get these guys going to phenomenal speeds. So let's do another exercise here. I want you guys to get out your calculators again, okay? So in this case, you can see I've just used a bunch of 9-volt batteries, but you can hopefully see that I could use as many as I want. What if I hook up so many of these? So the total voltage is 9 volts here, plus 9 volts here, plus 9 volts here, plus a whole bunch more. So the total voltage works out to be 500,000, which you might think is unrealistically high, but in fact, it's tremendously easy to do. It's not at all hard to get it. So the total voltage is 500,000 volts. So I want you guys to get out your calculators and tell me, what is the speed of that electron going to be if it has gone through a series of these guys where the total voltage of all of them added up together is 500,000? Okay, so Cohen is saying in the areas in between the guns, wouldn't the field work in the opposite direction? Yeah, but if you separate, well, actually, yeah, if you put them too close together, you have problems. But if you separate them by enough, so then when it's in between each parallel plate capacitor, the electric field outside of the parallel plate capacitor is a lot weaker than the electric field inside the parallel plate capacitor. So that's a great question. I'm glad you asked that. But I hope I answered your question. Ah, okay. I was wondering if anybody would notice that. Good for you, Josh. Okay, so Josh is very worried. Josh did this calculation right here, which I'll come to back in just a minute. And Josh got an answer which is faster than the speed of light. So yeah, it does appear that we just broke the laws of physics. Does that mean we can all go home? Oh, wait a minute. We are all home. Well, okay, what do you guys think? Have we just broken the laws of physics? Because this number that you get right here is, your math is correct. But obviously something went wrong somewhere. Anybody got any ideas of what went wrong? And it wasn't your calculation. Your calculation is good. What went wrong? What is it that we're not taking into account? It's by the way, I'll give you a hint. There is a law of physics that we have not yet studied in depth. It is something that I have mentioned several times. There have been many times where I have briefly mentioned this other law of physics, and every time I've mentioned it, I've told you, just relax, we'll get to it. We're not ready for it yet, but it's coming. What is it? So Josh is saying, is it unfair to combine all the voltages? Actually, it's not unfair to do that. Maddie is wondering if it's air resistance. No, it's not air resistance. Won't it just max out? Yeah, but why would it max out? Ah, okay, Cohen, you're on it. You got it exactly. Cohen is thinking that time slows down when you start moving quickly. Okay, which is very true. That's relativity. I've told you, you remember I have talked about relativity a lot. And I've talked about the fact that when you get on a spaceship and you start going at speeds like that are close to the speed of light, time slows down. But in addition to time slowing down, there's one other really interesting thing that also happens. Okay, and it's in addition to time slowing down. And I won't make you guess because I don't think you guess. Okay, in addition to time slowing down, another weird thing that happens because of relativity is that the mass increases. Okay, so if you look at this electron right here, okay, he's moving pretty slowly. So the equations that we use down here, okay, when we go plugging in the mass of the electron, we're going to, this one down here, we're going to plug it in as 9.1 times 10 to the negative 31. That's the correct number to use there. But now, as the electron passes through this parallel plate capacitor right here, the electron is now moving a lot faster than it was before. And that means due to relativity, which we will talk about later, don't worry, I promise I'll go into more detail. But the mass of that electron is no longer 9.1 times 10 to the negative 31. Because it is moving so incredibly fast, the mass of that electron has increased. Therefore, the amount of velocity increase that we're going to get will not be as much as we predicted. And when it gets over here, this baby is really moving. He's moving at a speed that's really close to the speed of light at this point. And that means his mass is most definitely not 9.1 times 10 to the negative 31 anymore. His mass is a whole lot more than it used to be. And so we're not going to get as much of a boost in speed as we would have predicted. So it's not that we didn't break the laws of physics, it's that there's another law of physics that we didn't take into account properly. And that other law of physics is relativity, which I promise you we will talk about. But before we get to it, there's a bunch of basic physics we need to learn first. Okay, so before I move on, let me just ask any questions about what we just talked about. I need to see a couple of yays or nays. No questions from Ian. Okay, all right, good. It looks like everybody's following along. Okay, good. Now, like I said, what we just talked about, it is in your book, but it's not in this particular chapter. They hold it off for a later chapter. But I think now is a good time to talk about it. Now, while all this stuff is still fresh in our minds about electric fields and parallel plate capacitors, I think it's a good time to do this. Okay, so for your homework tonight, I am not going to give you an assignment out of the book. I figure you guys, you've worked hard all week, you deserve a rest. Okay, so now I am going to give you the daily quiz. Okay, that's my way of taking roll. So I have to give a daily quiz every day. Otherwise, I don't have any way of taking roll. Okay, so I am going to post some questions on the daily quiz, very much like this one. So I trust that you guys took good notes. If you didn't take good notes, well, you're going to have to go back and watch the video. So as soon as we finish up here, Zoom starts processing the video, and it takes them anywhere between a half an hour to an hour to process it into the right form so that I can put it up on YouTube. So about an hour from now, the video will be online. So if you need to watch it, you can. But basically, I'm going to have questions exactly like this. I'm going to say, okay, I've got an electron gun. The voltage is such and such. So there's a lot of ways I could do this. I could ask you, what is the velocity of the electron that comes shooting out? I could ask you, what is the force acting on the electron? What's the electric field? And I might make it so it's not an electron. I might make it be a proton. Okay, wink, wink, nudge, nudge. So let's suppose that's a proton. What would we have to do different if that was a proton? Let's see what you guys have. So Spencer is asking, is there a way of calculating the mass of the electron at those high speeds? The answer to your question, Spencer, is definitely yes. And I promise you, we will do that. In just a couple of weeks, we will learn how to do that, but not right now. Okay, so I see that some of you are saying that if it's a proton instead of an electron, we have to change the mass. So you are absolutely right about that. Anybody got any ideas where I could find the mass of a proton? Google, yeah, Google works. Or the back of your book, okay? This page right here in the back of the book, all sorts of really useful stuff. This guy is going to be your friend from now on through the rest of the year You're going to be looking back here for a lot. There's one other really important thing that we need to do. These parallel plate capacitors, right now, they are oriented in such a way that they will accelerate the electron, but a proton has the exact opposite charge. So when we hook up our parallel plates here, we're going to have to swap the plus and minus sides on our voltages. So what we could do is we could just take the battery down here, and all we have to do is just flip the battery so that the left side is now the positive, the right side is now the negative. And then we also have to have some way to generate protons, but let's not get hung up on that. Okay, so other than the daily quiz, which is going to be a little harder today than usual, but not much, there's no separate homework assignment due tonight. So do I see any yays about that? Any claps or anything? Oh, secret word? Oh, that's a good idea. Yeah, we should probably do a secret word. Okay. All right. Anna, since you were the one that suggested it, you got any ideas? What would you like the secret word to be? Juniper 9. How about you, Anna? You're the one that suggested it. What would you like the secret word to be?
I'm not sure.
Okay. All right. So not sure. Okay. So that is the secret word. Actually, it's more than one word. It's a phrase, right? Okay. So that is the secret phrase for today. The secret phrase is not sure. Okay. So that might be a question on today's quiz. But don't forget, there will also be questions like this too. Okay, so, well, that's pretty much it. Kind of a short class today. Before I turn off the recording, does anybody have any questions? Wig? Why would I need a wig? I didn't make any mistakes today. Did I? Did I make a mistake that I don't know about? Okay. No, Yasmin, I'm not going to wear it. I only wear it if I legitimately screw up, and I didn't screw up today that I know of. Nah, that's peer pressure is not going to do it either. So, any questions? If I don't see any questions, I'm going to turn off the recording and end the class. So I'll give you just a few more seconds. Type in your questions. Okay, I don't see any. Going once, going twice. Sold. Okay, so